Alright, we're picking this up from the last video where we looked at the course overview, so we know that we're going to be talking about limits in this video. And to put some words down on the whiteboard, we say that if some function is defined near the value x being equal to a, then we can really introduce this concept of a limit, where we can have the notation that looks like this. So we would say the limit as x approaches a, for that function f of x, and if it's equal to something, we're going to call that q. Now q is just a placeholder, it could be whatever value you want, it could be no value, it could be infinity. But it's very important to note that x is not equal to a. Do not mistake the equal sign for this arrow here. Now in addition to this, we can have left and right hand limits. So we would have a left hand limit that would follow a similar format, except now instead of a, we have a with a little minus sign up here. So that minus sign represents coming from the left. And then we have a right hand limit. Again, similar format, except we get a plus sign, and now the limit is coming from the right. Now it's not always the case that the limit from the left is equal to the limit from the right. So as an example, let's consider kind of this oddball thing. We're going to say the limit as x goes towards infinity, or approaches infinity, of the function cosine of x. And we're going to ask what that is equal to. So we know that our cosine function oscillates like this, and it goes on forever. So as x goes to infinity, what is that value? And the answer to this may seem a little bit weird because, again, this cosine function goes on forever. So maybe there's not really a definite value we can assign to that. And that brings us into divergence and convergence. So if we look at convergence of a limit, kind of straightforward, it's going to converge to some value, but it's going to do that from both directions. And if this isn't the case, then we have divergence. So now the limit does not exist, that's what we would say. And again, we'd have that relation from up above, where the left hand and right hand limits don't match. But there's another type of divergence that's also important, and that's going to be the divergence to infinity, plus or minus we can have. And online, some people actually argue that divergence to plus or minus infinity is actually a kind of convergence, or it is convergent. I'll let the internet keep arguing about that, but in this course, we're simply just going to say that we would have divergence to plus or minus infinity. So we can look at that unit step function again, or it's also called the Heaviside function, and honestly I've seen them interchangeably used in textbooks. But we want to consider the limit as t goes to 0 for that Heaviside function, and we want to see what it is. So again, if we take the limit from the left, we get 0, if we take it from the right, we get 1. So what we could say is that this limit does not exist, or it diverges. So that's kind of the formality we would use. But we can actually have some useful rules with limits. So just a few of them are listed here. We can have the limit as x goes to a of f of x plus or minus g of x. You can simply just break that up, so you have the limit as x goes to a of f of x plus or minus the limit as x goes to a of g of x. If you have two functions multiplied together and you take that limit, you can break those up. If you have two functions that are being divided, you can break those up. You have a caveat though. You don't want to deal with this zero condition. And then powers and square roots, they'd follow a similar nature. And if you're having some intuition about this and you've seen similar things before for functions, well, it is kind of similar to if you were plugging in the value a instead of doing the actual limit, but that's not the case because we are not plugging in the value a. We are taking the limit. There is a distinction there. And let's say we want to find the limit as x goes to 0 of the absolute value of x divided by x. Now if we just try to plug in 0, we get this 0 over 0 condition, and that's bad. We always want to try to avoid that. So let's look at the left hand and right hand limits. We can kind of think of that as some really small value, call it epsilon, and epsilon can be tiny. And if we calculate this, we just get a minus 1, but if we take that right hand limit, again use some epsilon value, we get a positive 1, so you see here that those don't match. So because the left side limit and the right side limit, or left hand and right hand limits, don't match, again we get divergence. But now we get into a really important theorem that can help you if you're kind of stuck. And that theorem is called the squeeze theorem. So what this theorem says is if we have three functions, so we have f of x, g of x, and h of x. And in this theorem, we're going to be concerned about g of x. So if g of x is greater or equal to some f of x function, but it's less or equal to some h of x function, near the value that we want to plug in for the limit, and we can take the limit of f and h, and if those are equal to some value, let's call it q, well then the limit of g is also equal to q as x approaches a, because g is squeezed between these two functions here. So if we look at this in an example, let's look at the limit as x approaches 0, and then our function to investigate is x to the fourth, and then we have sine of 1 divided by x, and we want to know what that is equal to. So we know we have some multiplication right here, and we know that we could break these up, and this x to the fourth one is pretty easy to investigate. We know that will go to 0, but we don't know what this will go to. So if we look at the sine of 1 divided by x function as x goes to 0, well, we would end up with something that approaches sine of infinity. And we know from our cosine example that this is going to diverge. But the importance about this one is that this function is bounded. So what do we mean by bounded? Well, we know that the value of sine with any argument, that's going to be in the range from -1 to +1. So now what we can do with this inequality that we set up right here is multiply it by x to the fourth. So now we're left with this inequality right here. So in this case, right here on the left, that would be f of x. In the middle would be g of x. And on the right, that would be h of x. So we can take the limit as x goes to 0 of f of x and h of x. And that's pretty straightforward. We know that that's going to result in 0. And by the squeeze theorem, we know that g of x is going to be squeezed inside of here, so that is also going to be equal to 0. We probably could have cut some corners here once we knew that this limit was bounded and the other one went to 0, because 0 multiplied by something that is non-infinite, probably expect a 0. But just for proving out the squeeze theorem here, we went through this example. Now let's look at this same function, so x to the fourth multiplied by sine of 1 divided by x. But what we're going to do is change that limit. So instead of x going to 0, we are going to take x to infinity. So we don't have the full picture of limits yet. We actually need to get into the next topic, which is going to be derivatives. And then derivatives will actually unlock a pretty useful trick that we can use to solve this problem here. If you learned anything new or useful, please like, comment, share, subscribe. Helps the YouTube algorithm. Thank you for watching, and we'll see you in the next video.